Hi guys, this is Vicky here again. We are going to go through the 2014 Chem FRQ question number 2. And with no further ado, let's begin. So the question says propanoic acid is carboxylic acid that reacts with water according to the equation above. So this is the equation that we're looking at. At 25 degrees Celsius, the pH of a 50 milliliter sample of 0.2 propanoic acid is 2.79. Okay. So I'm actually just going to highlight some of the more important stuff. So that's that, this, and this. So numbers are always going to be very important when it comes to calculating for acid and bases. So A says, identify Bronson-Lowry conjugate acid-base pair in the reaction, clearly label which is the acid and which is the base. And if you guys remember Bronson-Lowry acid and base, it's just one proton difference, and that is the definition basically. Okay, so the acid is probably going to have one more proton and the base is going to have one less. So here, CH3, CH2, COOH, this is going to be the acid, and the one with one less proton is going to be its conjugate base. Okay, the other one would be water. Okay, so it'll be H2O versus H3O plus. Which one has one extra proton? H3O plus. So this is going to be the acid, and this is going to be its base. It just so happens that the product side is always going to be the conjugate. Okay. All right, let's continue to the next question. Determine the value of Ka. So easiest way to do this, okay? So we're looking at this equation right here. Okay, so that's going to be, the equation is propanoic acid plus H2O with the arrows H3, CH2, COO minus plus H3O plus. All right, so first of all, this is pure liquid, so we are not going to include it into our Ka equation, and this is a Ka. Okay, and remember Kas are always going to be products of a reactants, so CH3, CH2, COO minus, and then H3O plus over its reactant, right? So it's always products over reactants. So it just so happens that if you look, this is a 1-to-1 ratio. So if this is X molarity, this is also X molarity, right? Okay. We can actually figure out the concentration of H3O plus because they have given us the pH. So what is pH, guys? pH was negative log of concentration of H plus. And H plus is basically this right here, right? So the pH was 2.79 and it's negative log of H plus. So if I want to find out the concentration of H plus, it would be 10 to the negative 2.79. And if I were to put that into the calculator, I end up with 1.6 times 10 to the negative 3 molarity. Now that I have the molarity, okay, of H plus, which is essentially the same thing as hydronium ion, right? It's just that scientists are just lazy and we don't want to write all the full formula, right? So this goes in here, and because it's an X to X ratio, okay, this can actually go in there as well, right? And what is the concentration that we started out with? It was 0.2. So therefore, here I am going to write 0.2 molarity. And where did I get the 0.2 from? From there. Do you see that? Okay. So with that said, if I were to plug it in, I end up with 1.3 times 10 to the negative 5. And that is my Ka value. And remember, guys, Ka values, any K value has no units, right? It's got no units. Good. All right, let's continue with C. So C says, for each of the following statements, determine whether the statement is true or false. In each case, explain the reasoning that supports your answer. So the first one says the pH of a solution prepared by mixing 50 milliliter sample of 0.2 propanoic acid with 50 milliliter sample of 0.2 molarity of NaOH is 7. So here's the thing, easiest way to do this. Okay, if you're looking at propanoic acid, okay, versus sodium hydroxide, let's just quickly talk about their strengths. So propanoic acid, is that a strong or a weak acid? Okay, it's a weak acid, right? It has to be a weak acid because it's got carbon in it. Okay, do you remember from memorizing all the strong and weak acids in my previous video? Yes, so that's a weak acid, right? And NaOH happens to be a strong base. So if you have, okay, a strong acid and a strong base gets together and they're like fighting, which one's going to win? The strong one, right? So the solution ends up being more basic than neutral. Okay, so therefore this is a false statement. Okie dokies? Good. All right, let's continue to the second part. Okay, so that was 1. Let's continue to 2. The 2 says, if the pH of a hydrochloric acid solution is the same as the pH of a propanoic acid solution, then the molar concentration of hydrochloric acid must be less than the molar concentration of propanoic acid. Okay, so let's try to understand what the nature of a strong acid versus a weak acid does, okay? If you guys remember strong acids, okay, from my previous video, strong acids, they dissociate 100%, okay? They dissociate 100%. So if I have 5 molarity of HCl, I'm gonna have 5 molarities of H+. However, in a weak acid, less than 5% will dissociate, right? So less than 5% dissociates, which means that in order for me to have the same molarity, okay, the same molarity as this over here, I need a ton of them. So I need 100 of these to barely have 5% of the original concentration to dissociate. That means that if you look, I need to have 100 propanoic acids versus 5 HCl's, okay, to end up with the same amount of H pluses. And that's what a pH is, right? It's basically counting the number of H pluses in a concentration. So this question right here would be true. Does that make sense? Okay, cool. All right, let's continue to the next one. D. All right, so what does D say? D says a student is given the task of determining the concentration of propanoic acid solution of unknown concentration. A 0.173 molarity NaOH solution is available to use as a titrant. The student uses 25 milliliter volumetric pipette to deliver the propanoic acid solution to a clean dry flask. After adding an appropriate indicator to the flask, the student titrates the solution with the 0.173 sodium hydroxide, reaching the endpoint after 20.52 milliliters of the base solution has been added. Calculate the molarity of the propanoic acid solution. So basically, all we're looking at is this. So when they say that they have reached endpoint, that just means that the number of H pluses equals the number of OH minuses, right? So here's the easiest way to do this, okay? All we're going to do is, if you guys remember how to calculate acid and bases, okay, it's this, normality. You guys remember normality? Yeah. So this is normality for the acid and it's for the propanoic acid. It just so happens that I only have 1 H plus per 1 propanoic acid, right? And what about this one? Same idea. I have 1 sodium hydroxide per 1 hydroxide ion, right? So the number of moles of H pluses equals the moles of OH minuses. All right, so if I were to just plug in, I have 1 proton times, what is my volume? Do I know my volume? Yes, it's 25 milliliters, right? I have 25 milliliters of the acid. Has to equal, I don't know the molarity, right? Molarity times 25 milliliters of the acid has to equal 1, okay, one equivalence of hydroxide times what is the molarity of NaOH? 0.173, right? That is the molarity times, and what is the volume that when it reached equilibrium? It was 20.52, right? 20.52 milliliters. Okie dokies. So what is the new molarity? Okay, it was 0.142. So I need 0.142 molarity of propanoic acid to reach equilibrium. Okie dokies. All right, final one, E. E says the student is asked to redesign the experiment to determine the concentration of butanoic acid instead of propanoic acid solution. For butanoic acid, the value of pKa, so pKa for but is 4.83. This is for butanoic. The student claims that a different indicator will be required to determine the equivalence point of the titration. Based on your response to part B, do you agree with the student's claim? So, what was my pKa for propanoic acid? I believe they gave it to you, right? Yeah. So remember we determined the Ka value up here in B, and it was 1.3 times 10 to the negative 5. So what is P? P is always negative log, and because Ka follows afterwards, it's Ka, right? So negative log of 1.3 times 10 to the negative 5, and if I were to do the calculation, I end up with 4.89. Oh, look, guys, the pKa values of both are very similar to each other. They are so close to each other that we don't really need a different titration, a different indicator for the titration, okay? Because indicators can cover a plus or minus 1 range of the equivalence point. Okie dokies? And that's it. So I hope you enjoyed, and I will see you on the next video with the following questions. Cool. Thanks. Bye.